Today we're going to look at section 3.2, which is called polynomial functions and their graphs. So a couple of objectives, quite a few actually. We're going to identify polynomial functions. We'll recognize characteristics of graphs of polynomial functions. We're going to start determining end behavior. We're going to use factoring to find zeros, and we're going to identify zeros and their multiplicities. So, definition of a polynomial function. It says let n be a non-negative integer and let a n minus 1, all the way to a sub 0. They're going to be real numbers where that first term, a sub n, is not going to equal 0. So I know it looks kind of intense, but the function, it's just, you're dealing with, those a's in front are just coefficients or numbers that are in front. And then we're just talking about whatever x to the, say, like third power, then it goes x squared, then x. It's just going down each term until there are no more variables. Okay, we call this a polynomial function of degree n. All right, the number a sub n is the coefficient of the variable to the highest power. We call this the leading coefficient. All right, so we're going to determine which functions are polynomial functions, and then for those that are, we're going to identify the degree. So to be a polynomial function means that we are dealing with, like it says, we're dealing with all of these numbers. We're looking at variables, we're looking at exponents of those variables. So determining which one is a polynomial function. In number 1, when we have f of x equals 5x squared plus 6x to the third, it is going to be a polynomial. So yes, this is a polynomial. And the reason is because we are dealing with x's that have positive integers as their exponents, okay? So we always identify the degree as the highest exponent. So in this problem, even though x squared is first, x to the third, the 3 is the biggest exponent. So we would say that this is degree 3, which is technically called then a cubic, okay? But it's a polynomial because all of the terms have exponents that are positive integers, okay? So then that brings us to the next problem where I have g of x equals x to the 1/2 power minus 3x squared plus 5. This right here, because I have a fraction for an exponent, that tells me that this is not a polynomial, okay? I want integers, so we're thinking about numbers on a number line, but I only want positive integers. So if that was like a negative number, not a fraction, but a negative number, it also would not be a polynomial, okay? So then I'm not going to identify the degree since it's not a polynomial. All right, so polynomial functions. To determine if a graph is a polynomial function, the graphs must be smooth and continuous. So if you look at the left side of the pictures versus the right side, on the left side, everything's nice and smooth. So there's no like V's or anything. It's all like U's and W's and all that kind of stuff. So nice, smooth, it's all connected. But if you look on the right, there is the graph that's dealing with, it's kind of 2 graphs in one because it's broken up. Anytime it's broken up, it's not a polynomial function. Like I said, any sharp corners like a V also means that I do not have a polynomial function. All right, so we're going to identify which one of these graphs are not polynomial functions. So if I look at number 1, hopefully we notice that there's kind of this sharp curve right here. So this means that it is not a polynomial. If I look at the second picture, I see that there are 3 different portions to this graph and they're being broken up. So anything that's broken up means that it is not a polynomial. Oops. And then if I look at this third graph, because everything is continuous, everything has nice smooth curves to it, this one actually is a polynomial. So actually the second picture is something that is called a rational equation or a rational graph, and we're actually going to be graphing those later on in this chapter. Number 3, this picture right here, is actually a graph of a trig function, and that's something that we'll do second semester. All right, let's talk about end behavior. So end behavior of a polynomial function. The behavior of a graph of a function to the far left or to the far right is called its end behavior. So we have something called the leading coefficient test that's going to help us determine the end behavior. So if n is odd, okay, so if our exponent, the biggest degree, is an odd number, if the lead coefficient is a positive number, then the graph falls to the left and rises to the right. Okay, so in this example here, notice that I know that, so basically it's kind of like, think of like a cubic function, okay, degree 3, that's an odd. If there is no negative in front, so there's no reflection, we always had the graph starting on the left going down and then ending on the right going up. So it rises on the right and it falls on the left. If the lead coefficient is negative, meaning that we have that reflection, then it's going to flip. It rises on the left and it falls on the right. So then if we have n as an even number, so we're thinking like x squared or x to the fourth, something along those lines. If the leading coefficient is positive, the graph is going to rise on both the left and the right side. I mean, the easiest thing to remember would be like our quadratics that we've been graphing, okay? That is an even number. It's x squared. And remember, when the a was positive, which is our lead coefficient, the graph opened up on both sides. But if it was a negative, then we had it opening down on both sides. So that's why if the lead coefficient is negative, the graph's going to fall to both the left and the right. All right, so we can look at this without having to have it actually graphed to determine the end behavior. So we're using this lead coefficient test. So once again, there's two things that we have to look at. We have to look at the degree, and we have to look at the lead coefficient. That information is going to tell us what our end behavior is. So if the first problem says f of x equals x to the fourth minus 4x squared, the biggest exponent is a 4. So if it's degree 4, that makes it an even number. And so because it's an even number, that means it's either going to be both sides heading up or both sides heading down. The lead coefficient is the number that is in front, and if I don't see a number in front, then it's a positive 1. So I have a positive number. So positive numbers, even indexes, so that or even exponents, that tells us that we are going to be rising. So it rises to the left and the right. So both sides, it's going up, it's rising. Okay, if I look at the second example, g of x equals negative 2x to the third plus 8. So we have to look at what the degree of this polynomial is and what is the lead coefficient. So it looks like there is only one exponent here. It's a 3, so that makes it an odd number. So that tells us that one side is going to go up and one side is going to go down. If I look at the number that's in front of that, it's a negative 2. So we're dealing with a negative number. Okay, so when we're dealing with a negative number, that tells us that we are going to rise on the left and we are going to fall on the right. Okay, because it is technically a cubic graph. Remember, our original x cubed would look like this, but because there was a negative in front, it was that reflection. So notice that It got flipped around. That's why it rises on the left and it falls on the right. Okay, let's talk about zeros of polynomial functions. If f is a polynomial function, then the values of x for which f of x equals 0 are called the zeros of f. Okay, so essentially these values of x we can call roots, solutions, zeros. You've got all of those vocab words that essentially mean the same thing. So zeros, roots, solutions, it's when you set the polynomial equal to 0 and solve for x. So if I'm asking for us to find all our zeros for f of x equals x cubed plus 2x squared minus 4x minus 8, what I'm going to have to do is I'm going to have to set that equal to 0 and solve. So x cubed plus 2x squared minus 4x minus 8 equals 0. Because there are 4 terms and none of those are like terms, we are going to have to factor by grouping. So I'm going to group the first 2 terms together. I'm going to group the last 2. I had to keep the negative with the 4 because I always want an addition sign breaking them up. I'm going to factor out each of the parentheses GCF. So in the first parentheses, x squared is what they have in common. That leaves you with an x plus 2. In the second parenthesis, they both have a negative 4 in common, which leaves us with an x plus 2. Remember, if I'm factor by grouping, if I don't end up with the same thing left over in parentheses, then it's either not factorable or you made a mistake. So that means that now I get to take out what they have in common, which is the x plus 2, which leaves you with the x squared minus 4. We could technically keep factoring the x squared minus 4 because that is a difference of squares. X squared is obviously a squared term. 4 is a squared term. So technically then I can factor that into x plus 2 times x minus 2. Because this is an equation and I am solving for x, I get to set each factor equal to 0. So x plus 2 equals 0, x plus 2 equals 0, x minus 2 equals 0. Well, because the first 2 equations are essentially the same, we only have to solve that one time. So if I subtract 2 from both sides, it looks like one of my zeros is that x equals negative 2. And like I said, I don't have to list that twice, even though I have 2 zeros that are the same. And then over here, I'm going to add 2. And so 0 plus 2 tells me my other number is 2. So here are my zeros. Technically, because this is degree 3, we should have 3 solutions. And I do have 3 solutions, except one of them is repeated. So that's why I only had to write it twice. But it is important to note, okay, whatever the degree is, that's how many answers I should have. And so if I can't figure out that I have that many, then we're going to have an issue. But in this case, because I know that one of them is repeating, that's why I only have 2 of them, we're good to go. Okay, so then let's try this one. So we're going to find all the zeros of f of x equals x to the 4th minus 4x squared. So once again, to find our zeros, I'm going to set that equal to 0 so I can start solving for x. So I'm going to factor. The first thing I'm going to do is look for a GCF. Both of those have an x squared in common. So then that leaves us with an x squared minus 4 in parentheses. We just did a problem where, okay, x squared minus 4, that's a difference of 2 squares. So I can actually continue to factor. That turns into an x plus 2 times an x minus 2. I've factored as much as I can, so now I need to set each factor equal to 0. Notice that because this is degree 4, that means I should have 4 solutions. Well, notice that if x squared equals 0, to get rid of the square, I'm going to take the square root. Normally, when you take the square root of 2 or of both sides of an equation, you get 2 answers. You get both a positive and a negative. However, the square root of 0 is going to be 0, and there's no such thing as a positive 0 and a negative 0. So there are 2 zeros, so I'm only going to have to write it one time, but I do have 2 solutions there. Notice over here, I would then subtract 2. Over here, I would add 2. So that means that also negative 2 and positive 2. So I do have 4 solutions because 0 was repeated twice. So those are all my answers. All right, let's talk multiplicities. So multiplicities of zeros occur when the x-intercepts repeat. And so actually, both of the examples that we just did, we had answers that repeated. Okay, so x-intercepts, the same thing as zeros, same thing as solutions. Okay, so when they repeat, we call these that we have multiplicities of 0. So multiplicity provides a connection between the zeros and the graphs. So there's a couple of scenarios. If we have an even multiplicity, then the graph touches the x-axis and it turns around at that 0. If we have an odd multiplicity, then the graph crosses the x-axis at that 0. So when I say even multiplicity versus odd multiplicity, that means even multiplicity, I have 2 of the same number or 4 of the same number. So I have an even amount of the same number. When we're talking odd multiplicity, that means that that number repeated 3 times or 5 times or even just once. Okay, so then it's depending on, am I going to touch and turn or am I going to cross through the x-axis? So here's an example where we're going to find the zeros and state the multiplicities of each 0 and then state whether or not the graph crosses or touches and turns at the x-axis. So everything is already factored for us. All we have to do is set each of those factors equal to 0 in order to start solving for x. So the -4, because there are no x's, I don't have to set that equal to 0. But what I have in parentheses, x plus a half, I want to set that equal to 0. So x plus 1/2 equals 0. So I can then very easily solve for x. I just need to subtract a half. So x equals -1/2 is one of my zeros. Now, because it was quantity squared, I really technically have that parentheses 2 times. So I was really having to set that equation equal to 0 2 different times, but it results in the same answer. So this actually then tells me that I have a multiplicity, if I can spell, multiplicity of 2. Okay, so it says give the multiplicities of each 0. So that's one of my answers. Because I have that exponent of 2 that tells me that equation technically needed to be righted twice, I have an even multiplicity, a multiplicity of 2. The next factor is x minus 5. I get to set that equal to 0. So I just then have to add 5 to both sides. 0 plus 5 is going to give me 5. And so that is my other 0. Because it had an exponent of 3, I technically had to solve that equation 3 times. So that means I have 3 of the same number. So that means that for 5, I have a multiplicity of 3. Okay, so with all of my zeros, one of them has an even multiplicity, one of them has an odd multiplicity. So remember, the graph is going to cross the x-axis at 5. And the reason why it's crossing at 5 is because that was an odd number for multiplicity. So it always crosses the x-axis at an odd multiplicity. And because that -1/2 is an even multiplicity, it's going to touch and turn at -1/2. Okay, so all of this was an answer. And then all of this was an answer. Okay, so I stated the zeros, stated the multiplicities, stated if it crosses or touches and turns. Let's take a look at another example. This time I have the function f of x equals 4x cubed plus 3x squared minus 16x minus 12. And I want to state the multiplicities of each 0 and then tell if it touches or if it touches and turns or if it crosses. Okay, so this time it's not already factored, so I'm going to have to factor in order to start solving for my zeros. All right, so because there are 4 terms, I'm going to factor by grouping. So I'm going to group the first two. I'm going to group the next two. Notice I have to keep the negative with the 16 because I always want an addition sign breaking them up. So in the first parenthesis, it looks like x squared is what they have in common. And so that leaves me with a 4x plus 3. Then in the next parenthesis, it looks like they have a negative 4 in common. So that leaves us with a 4x plus 3. Remember, in order to factor, I need to have that parentheses be the same. So then I can factor out that GCF of 4x plus 3. That leaves us then with x squared minus 4 in the other parenthesis, which once again, that's a difference of 2 squares. So I can continue to factor that into x plus 2 times x minus 2. And then I can set each of those equal to 0. So we've got 4x plus 3 equals 0, x plus 2 equals 0, and x minus 2 equals 0. So I'm going to subtract 3 from both sides. I'm going to divide by 4. So it looks like one of my answers, x equals negative 3/4. And if we notice that none of those that I factored have an exponent, so it technically has an exponent of 1. So I'm only having to set that equal to 0 one time. So that's going to be a multiplicity of 1. Okay, if I look at the next equation, I'm subtracting 2 from both sides. So that gives me x equals negative 2. I only had to set x plus 2 equal to 0 one time. So I have another multiplicity of 1. And then in this last equation, I had to add 2 to both sides. That gives me x equals 2. I only had to set that equal one time. So all 3 of these are a multiplicity of 1. And that makes sense because my solutions, I should have 3 of them. And so since I do have 3 different numbers, I can only have a multiplicity of 1 because if one of them had a higher multiplicity, that means that I had more than 3 solutions, which isn't possible here. So all of this is my answer. But then I also now need to tell whether or not the graph crosses or touches and turns. Now, because all of those have an odd multiplicity, the graph is going to cross at each of those numbers. So the graph crosses the x-axis at, and then it's all 3 of them. So negative 3/4, negative 2, and 2. All right, I would suggest that you pause the video and do the checkpoint problem. So there's 2 parts to it. First, I want you to use the lead coefficient test to determine the end behavior. And then I want you to find the zero, state the multiplicities, and then tell whether or not the graph crosses through the x-axis or touch and turns. All right, so notice that we have an odd degree because it's 3 and a positive lead coefficient. So that means that it's going to fall to the left and rise to the right. So there's my end behavior. I set that whole thing equal to 0. I have 4 terms, so I factored by grouping. I got then x minus 5 times x squared minus 25, which technically x squared minus 25 can factor into x plus 5 times x minus 5. So I have 3 factors, 2 of which are the same. So when I set each of those equal to 0, I have a multiplicity of 2 for the number 5 and a multiplicity of 1 for the number negative 5. So there's 3 numbers there, which is good because this is degree 3, so I should have 3 solutions. So because I have an odd multiplicity at negative 5, it's going to cross through. And because I have an even multiplicity at positive 5, it's going to touch and turn. And that's all of our objectives.